So our next speaker is Xander Faber, who will talk about totally T-adic functions of small height.
All right, thank you very much. So I'd like to thank the organizers for the opportunity to speak. So I was a postdoc in Montreal, I guess over a decade now at this point. So it's always a pleasure to come back to Quebec. As a sort of preliminary story, this is the first Quebec-Maine number theory conference that I've ever been able to attend. So typically in the middle of September, I go on a fishing trip in Ontario with some members of my family and a few other people from the town I grew up in. And so I sort of burn all my husband points in the middle of September, and then I don't have any left over to go to conferences towards the end. But this year I didn't get to go on that trip because the Canadian border is closed. So I get to come to this conference. Thank you for having me. All right, so let's see. There we go. So this is joint work with Clay Pecci at Oregon State, and this was recently accepted for publication. It was interesting publishing with an Italian journal during this period of time. All right, so let's start out with a discussion of totally real algebraic numbers, just to sort of set the stage by analogy. So many of you know what totally real algebraic numbers are, but if not, a nice way to think about them is to say that an algebraic number is totally real if its minimal polynomial splits completely over the reals. Right? So this is not typically how people say this. Often people will say, when you look at all of its embeddings into the complex numbers, all of those land in the real numbers. But that's equivalent to this. Right? So a typical example is real quadratic fields, or even more concretely, something like a plus b root 2 for a, b, and q. Right? Both of the conjugates are real. So there's this delightful result of Schinzel that says if you throw away some obvious cases where this is false, then the height of a totally real algebraic number is bounded below by this quantity. And there are two things of interest here. The first one is that this is positive. So totally real algebraic numbers can't have their heights be too close to 0. Okay, so this is interesting. And the second thing that's interesting is that this bound is sharp, which is to say that there is an algebraic number that realizes this, and in fact, it's the golden ratio. Okay, and Schinzel proved this by looking sort of at the explicit geometry of roots of polynomials, totally real polynomials, and you obtain something like this. So, but morally, it's nice to know why a result like this is true. And so the way I like to think about this is that there's this result of Yuri Bilu that says that if you have a sequence of algebraic numbers, and if their heights, distinct algebraic numbers, and if their heights tend to 0, then those numbers, or at least their Galois conjugates, the full Galois orbit of such numbers, they like to distribute themselves around the unit circle in a complex plane. So you take an algebraic number, you plot all of its Galois conjugates in a complex plane, and if the height of that number is fairly small, then it's going to look like it's well spaced around the circle. Or said another way, things with small height like to look like roots of unity. Okay, so I've plotted the roots of a random irreducible polynomial of degree 49 here with 0, 1, and -1 coefficients, and it turns out to have fairly small height. So back to totally real numbers. So why can't totally real numbers have small height? Well, the reason is that all of their conjugates are stuck in the real axis. They can't equidistribute. Okay, so there it is. They can't have small heights. All right, so continuing with this analogy, let's talk about totally p-adic algebraic numbers. So a number is totally p-adic if its minimal polynomial over q splits completely over qp. So this is my analogy with a totally real case. Another way to think about this is a little more number theoretic, if you like, is that p splits completely in the number field generated by alpha. Okay, so the ideal p splits completely into residue degree 1 ideals in here. Okay, so here's a nice example. So I use a plus b root 2 again, and this is actually totally p-adic for p odd when the Legendre simple 2 on p is 1, because then 2 is a square in qp. So this is totally p-adic. So there's this analogous result to the Schinzel result that was proved by Bombieri and Zanier, that if you throw away the case where you're looking at p minus first roots of unity or 0, then an algebraic number is totally p-adic. If its height is, if it's totally p-adic, then its height is bounded below by some quantity depending only on p. This quantity comes out of a later result. This was improved by Paul Feely, Clay Pecci, and then an idea of Clay Pecci that Lucas Pottmeyer ran with gives this lower bound. Okay, but notice that I don't say it's sharp in this case. We don't actually know what the sharp lower bound is. We don't know if the lower bound is attained by an algebraic number, and so we know very little about the So again, we have a sort of moral reason why this is true. There's this collection of equidistribution results that were proved around, I think, 2004 by Matt Baker, Bob Bromley, and then there's another paper by Antoine Chambert-Loire, and then another paper by Xander Faber and Wander Letelier. It says that you have a similar equidistribution result to the Beeler result, where if you take a sequence of algebraic numbers whose heights tend to 0, and you plot their Galois orbits in an appropriate space, then they tend to equidistribute according to some measure. So what is the space? It's the Berkovich projective line associated to CP, right? The completion of an algebraic closure of QP. This ought to look like a Bruhat-Hitz tree. There's a very good reason for that. The Bruhat-Hitz tree actually embeds in this. And then the measure is what's called the discrete mass of the Gauss point. So they're equidistributing to this central point. And what does equidistribution mean in this case? It means that the Galois orbits tend to spread out among the branches. Okay, these branches are in one-to-one correspondence with elements of P1 of FP bar. So why can't totally p-adic numbers be equidistributed? Well, the reason is since they're totally p-adic, they're stuck in the FP rational branches, okay, in the sort of classical Bruhat-Hitz tree. And so they can't spread out among the branches. Okay, so that's the moral reason why you should get a height lower bound. Okay, so I guess I could keep putting slides up like this with equidistribution results for the rest of the talk, but we're going to go a different direction. So I think it was the tail end of last year, maybe last summer sometime, Clay Petchy and I were communicating via email, and rather than give the whole thread, I just put together a dramatic reenactment for you here. And the basic idea was that Clay had this idea for obtaining sharp lower bounds for heights of totally p-adic numbers. We don't have a sharp lower bound in that case. And we kind of went back and forth on this, and kind of the upshot of it was, well, it seems like it's not a bad idea, but it also seems really technically difficult. And so I threw out this idea, maybe we can prove something in the geometric case. We switch to function fields where we have some nicer tools and we don't have to deal with our median places and see what we can do, okay? By the way, for anybody paying attention in the US, I was rather proud of the mobile carrier that I put together for this dramatic reenactment. Okay, so let's talk about function field heights. There's sort of a lot going on in this slide, so I'm going to kind of guide you through the highlights. So first of all, we're going to let K be a function field, which for me is going to be a finite separable extension of FQ of T. Right? Now, plugging the geometry in immediately, what we know is that K is the field of rational functions of some smooth proper curve over FQ, right? And writing down this extension actually gives you a map from C to the projective line, okay? The places of K, the valuations on K correspond to points of C, right? So given a point, you get the measure of vanishing of a function there, and that's what the valuations all look like, all right? This bullet is here for anyone who knows and has worked with heights of algebraic numbers. This is the local decomposition of the function field height. I'm not going to use that description. I'm going to use a different description of the height, which I'll describe in just a second. But I wanted to say that if you know about heights of algebraic numbers, then they behave in very similar ways. But there's a nice sort of other way to think about them. It looks like this. So if you have an element of your function field K, well, that's an extension of FQ of T, so I can write down its minimal polynomial over FQ of T. So it's got rational function coefficients. Okay, but I can clear out denominators in the same way I clear out denominators for rational minimal polynomials, so I can get an integer minimal polynomial. So in the same way I can get polynomial coefficients. So I can view this minimal polynomial as a polynomial of two variables, T and X. All right, so minimal polynomials of these function field elements will be bivariate polynomials. Then it turns out that you can just kind of massage this formula and learn that the height of alpha is exactly the T degree of this polynomial over the X degree. So the X degree is exactly this quantity, this degree of the function field extension, provided that alpha generates the function field. And then the T degree is somehow measuring the polar divisor in here. Okay, so that's what's going on. So we'll use this definition for this talk. And then it's rather comforting to know what the elements of height 0 are. They're the constants. Okay, so the elements with that are in the constant field, as well as infinity, because we consider that a constant. Okay, so in order to have non-zero height, you have to have an honestly varying function, so not a constant function. All right. So what is a totally p-adic function? So analogy, we'll say an element in the separable closure of FQ of T is totally T-adic if its minimal polynomial splits completely over the Laurent series FQ of T. Right? So this is the completion of FQ of T at the T-adic place, right? Or vanishing the order of the place that measures the order of vanishing in 0. Okay. So if we look at the minimal polynomial of FQ of T, that splits completely over the Laurent series field. Or equivalently, it's to say that the ideal generated by T downstairs splits completely in the function field. Okay. So there's a number theoretic description of it. So here's an example. If you decide to sort of check out at some point, it's fun to try to prove for yourself why this thing is totally T-adic. So you need to show that it has Q+1 roots over the Laurent series field, and that's exactly Hensel's lemma is going to give you that, provided you apply it correctly. Okay. So here I've got Q odd and C as a non-square. That's what's going to guarantee a reducibility of this thing. I will say that I do have examples when Q is even as well, and they're of a similar flavor. Okay. So here's the main theorem that we prove in this paper. So if you have a totally T-adic function, and it's not a constant, then its height is at least 1 over Q+1. Notice it depends only on Q and not on anything else that's in the picture. And this bound is sharp. We can give examples, and in fact, the roots of this polynomial actually do have height 1 over Q+1. You can see that the T degree of this is 1, and the X degree is Q+1. Okay. So I give this sort of pithy proof of it in haiku form. The idea is that you rework Pottmeyer Archimedean places, not in function fields. Basically, you just look at the part that sort of messes up the sharpness in the argument, and you observe that's not relevant in Pottmeyer's proof. Okay, so that's sort of pleasant, and I'm kind of making light of some of the technical details here. But this was the first proof that we gave, and it was unsatisfying because the whole point of starting this project was that we could use the geometry. So here's a geometric proof. So let's start out with the minimal polynomial for a totally T-adic element alpha. Okay, so I'm going to write that as a bivariate polynomial, T and X. And that's the vanishing of that will define a plane curve, call that F equals 0. And then if you take the normalization the closure of that, you get a smooth proper curve. It's birational to that thing. So we'll call that C. Here's a schematic. And because I have these two variables, T and X, they actually define functions on my curve C. Okay, functions to the projective line. So I've got a curve and two distinguished functions on it. And let's define their degrees to be D and N. So D is the X degree, N is the T degree. And there's a reason for this. Remember, the height is T degree over X degree. So N numerator, D denominator, keep it straight that way. And what we're going to do is we're going to use this picture to estimate the number of rational points on C. Okay. So the way we'll do it is this. So let's first look at the T map. So the T map has, the degree of this is the number of points over a given point downstairs. So when I fix T, I just get a polynomial in X, and I said this thing has degree D. So this map has degree D. Okay. Well, the T map has the property that over T equals 0, I have complete splitting, or said another way, I have all rational points over top of T equals 0. That's what the totally T-adic condition buys us. T equals 0, or T splits completely upstairs. So that means I have D rational points above T equals 0. Okay, so that's a lower bound for this. So that gives me a bunch of rational points in one fiber, all right? But of course, that's a lower bound. So what about the other map? The other map, when I fix X, this becomes a polynomial in T, and so I see that this map has degree N. And there's a cute way you can use a map of degree N to bound the number of rational points, and it goes like this. Every rational point upstairs maps to a rational point downstairs, and every rational point downstairs has at most N rational points upstairs, where N is the degree of this map. Okay, and so all I need to do then is say the number of rational points upstairs is at most N times the number of rational points downstairs. Well, this is the projective line, so that's Q+1. So I get an upper bound of N times Q+1. I say this is a trivial bound. I'm using the fact that I have a morphism to buy this for me. Okay. And now what I do is I just look at the inequality that's given here and solve for N over D. Okay, perfect. Now, if you stare at this, though, this actually gives you a neat geometric condition for having minimum height. So in order to have minimum height, it has to be true that all of the rational points on P1C lie above t equals 0. And it has to be true that every point over a rational point of P1 is a rational point. There's two very strong conditions. So all of the rational points live above t equals 0 on this, right? So they're all sort of in a line above this. But then they're sort of equally spaced out above P1 for this map, right? And it turns out that you can run these conditions backwards and get a geometric characterization of minimum height elements. So there's kind of a lot going on in this slide. So I'll just say the picture we drew on the previous slide, suitably interpreted, implies that you have a minimum height totally t-adic element. So you have two functions on your curve C, which generate the function field, right? And one of those maps has degree nq plus 1, the other one has degree n. It turns out that this parameter n in here is the gonality of this curve, if you know what that means. Okay. And then the number of rational points has to be n times q plus 1, and the function t has to kill all of those points. So that's the list of conditions we just laid out in the previous slide. And if you have all of those, then X generates a totally t-adic extension of fq of t, and it has minimum height. Right, so that's delightful, and this actually gave us a nice window into how to construct additional examples with larger gonality than 1. So for example, if n divides q minus 1, then you have q minus first roots of unity in your field, then you can construct cyclic n covers of P1 like this. Okay, these very simple looking curves. And then you just write down this other function t that has the right property. It kills all the rational points of your curve, and now you find that the function x is totally t-adic of minimum height. This is a really nice way to construct examples. Okay. Now, I am a person who likes to construct examples in sort of as varied a fashion as I can to understand what's going on. And after we wrote down these geometric ones, we kind of got stumped. We couldn't figure out how to construct examples where n was bigger than or equal to q. This is limiting, so you need q minus first roots of unity to use this method. And I wanted examples where n was large, the gonality was large relative to q. Well, I'm getting ahead of myself. So I'm not going to belabor this slide, but you know, when you write down a curve, of course, you start asking questions like, what's the geometry of this curve? So you can estimate the genus of your curve associated to a function, a totally t-adic function with minimum height. You can get a lower bound by using the Vey bound. Right? The Vey bound gives you an upper bound on the number of rational points, and since we know the number of rational points, you get a lower bound of the genus. And if you know anything about the Vey bound, then for various curves, it's not at all sharp. And so this is not a particularly sharp bound. The upper bound, you can use Castelnuovo's estimate, which amounts to the adjunction formula on the surface P1 cross P1, and then control the singularities of it. I'm not going to go into details of that, but the point is you can say something about the genus of these curves. Okay. All right, so as I was saying, I wanted to construct more examples of minimum height elements. And so it helps to go back to Pottmeyer's argument that we modified to try and understand what else you can say about these totally t-adic functions. And it turns out, and you can see this in the geometric picture too, but it turns out that if you write down the minimal polynomial of one of these totally t-adic functions of minimum height, the Galois conjugates are sort of well distributed among residue classes, FQ rational residue classes. Now they can't be really well equidistributed for these kinds of p-adic equidistribution result reasons, but they're sort of as well equidistributed as they could possibly be given the constraints they have on them. So here's what happens if you factor one of these minimal polynomials over the power series field. What you find is that you've got n roots. Okay, so this is the gonality n example. Here you have n roots that are near infinity. And then for each element of FQ, each constant, you have n roots that are near u, okay, that look like u modulo t. So that's what you can tease out of the proof that an element has minimum height, a totally t-adic element has minimum height. So this gives you a way to factorize that. But now this actually gives you a search space if you wanted to look for examples. So what you can do is you can write down power series AI and BUI and truncate them at a certain point, because you know that ultimately this is a polynomial of degree n in t, okay? And so that gives you finally many coefficients to vary through here. And so we just wrote some Sage code that would sort of loop over all of these, check to see which ones split completely over the Laurent series field and are irreducible, and that gave us some new examples. So for example, we found a gonality 3 example over F3. There it is. I don't find that so enlightening, but I thought I would write one down just to be concrete. But a thing that did come out, and this was really interesting to us, was that by hand, we could show that over F2, there were no examples with gonality 2. There were no examples with n equals 2. And you just kind of write down all the conditions you can think of, and it sort of rules everything out. The only things that are left either don't split or are reducible. And so then we ran the SAGE code against the case n equals 3 and found that there were no examples in that setting. And it seemed just close enough that we might be able to do it for n equals 4. And it turns out that it was. We had to apply a few more tricks. And the search space was still a little too big. There was something like 2 to the 25th polynomials, which feels like not too many. But you have to factor all of these. And factoring over a Laurent series field is not particularly fast, especially because these things have very large, very divisible discriminants. And that makes it so you can't just apply something like Dedekind's criterion to factor these. And so what we did was, so I distributed the computation among 32 computers at my office, ran SAGE on 32 machines, and it took about a day. So that's about a month of wall clock time to prove that there were no examples over F2, n equals 4. This is tantalizing. I mean, it's only 3 data points, but it does feel like maybe you might want to make a conjecture. Okay. All right, I think I'm about out of time, so I'm going to skip over this slide. You can think about elements of small height as well, not just minimum height elements. So that's certainly an interesting place to go for future work is, what if you consider things of small height, things where you're not at the minimum, but maybe near the minimum, right? Is the minimum a limit point? Are there infinitely many totally T-adic functions that achieve the minimum? And then, of course, there's the question of if Clay's original idea, the potential theory approach, actually plays well with the geometry. Okay. All right, I think I'll stop there. Thank you very much for your attention.